Alright, so we're picking up with the rest of chapter 4. So our first couple examples were Newton's second law in one dimension, but we have forces in this case that are going to be acting in two dimensions. So Newton's second law is a vector equation, so we're going to have to account for the forces acting in both the x and y direction. So I like this problem because it's got a couple concepts that you're going to see fairly often. First thing is this first sentence says a traffic light's weighing 112 newtons. So what they're doing is they're giving us the weight in newtons. Alright, so if I say the weight of something is whatever newtons, I already give you the gravitational force. Alright, so I'm already giving you the weight force. This isn't the mass of the stoplight. This is actually the force of gravity on the stoplight. So I don't have to multiply this by g or anything like that. It's already in newtons. It's already a force. So it's hanging from a cable we're calling T3. And it's fastened by, we'll call this a knot or something. It's fastened to two other cables, T1 and T2. So these two cables make angles of 37 degrees. We'll say theta 1 is 37 degrees, theta 2 is 53 degrees. Okay, so these two cables are making angles with this ceiling or this pole, whatever it is, at these two angles. So these two cables, T1 and T2, have a tension rating that should not exceed 100 newtons. So basically what we have to do is we have to find the tensions in these two cables and then see if they exceed 100 newtons. Right? The question is, does the traffic light remain hanging in this situation, or will one of the cables break? So we have to find T1, T2. We actually have to find T3 as well, and I'll show you why in a little bit. So we have to see if T1 and T2 are less than or greater than 100 newtons to answer this final question. So I've got free body diagrams for two things. I've got a free body diagram for the stoplight. Go back to the stoplight. Draw a little box around here. That stoplight is experiencing two forces. It's experiencing T3 in the positive y, holding it up, and it's experiencing the gravitational force, because it's close to the surface of the earth, in the negative y direction. So my free body diagram looks like T3 in the positive y, and F sub g in the negative y. Again, we were given the weight at the start of the problem in newtons. So I know this weight force is just 122 newtons. Alright, T3 in the positive y, F sub g in the negative y. The net force on the stoplight is 0. Alright, the net force on the stoplight is 0. Alright, because it's being suspended from a cable. Alright, and it's motionless. It's not like swaying in the breeze or moving up and down, anything like that. So it's stationary, which means it's not accelerating. Its motion is constant, so the net force is 0. So I write Newton's second law, T3 in the positive y minus F sub g, right? Just like I did with the diver in the bucket. Gravity's acting in the negative y, T3's in the positive y. Add them up, set them equal to 0 in this case, because the stoplight's stationary. Add F sub g to both sides, we see that the tension in T3 is the same as the gravitational force on the stoplight, 122 newtons. Okay, so we've got T3. I'm going to draw another free body diagram. I'm going to draw a free body diagram of this knot right here. Because T1 and T2 aren't acting directly on the stoplight, T1 and T2 are acting at this location where the three cables meet. So I'm drawing a free body diagram right here where the cables meet. So I've got T1 acting in this direction, T2 in that direction, and then T3 pulling straight down. Right? T3 was positive because it was holding the stoplight up over here, but it's negative because it's pulling down on the knot. It's in contact with that location, and the tension is in the negative y direction. Alright, how do I know that I can label these two angles theta 1 and theta 2? I got to go back to our old geometry days. Okay, so if you draw a line through that knot that's parallel to that pole, alright, so the pole goes like this, it's in the x direction, we'll draw another line parallel to the pole going through the knot. So this is the pole, this is the line that I drew going through the knot. Theta 1 and theta 2 are marked in the diagram up here, right? Theta 1, theta 2. Alternate interior angles are congruent. If these two lines are parallel, these are parallel lines, this pair of angles here are what we call alternate interior angles, and they are congruent. So if this is theta 1, this angle right here is also theta 1. T1 is pulling in that direction, so there's theta 1. Same thing with theta 2. Theta 2 is pulling up in this direction, okay? Or T2 is pulling up in that direction. We've got theta 2 up here, another pair of alternate interior angles there congruent, okay? So theta 1 is the direction of T1 in my free body diagram. Theta 2 is the direction of T2 with respect to the x-axis, okay? So now that I've got forces in the x and the y direction, I actually have to write Newton's second law in the x and the y direction. So I'm going to write two separate forms of Newton's second law. First thing I do is I resolve T1 and T2 into its x and y components. All right. So the x component of T2 is T2 cosine theta 2. The x component of T1, T1 cosine theta 1. Similarly with the y components, T1 in the y is T1 sine theta 1. T2 in the y is T2 sine theta 2. Alright, just like we did with vectors last chapter, I've got the x component cosine theta 1, the y component sine theta 1. Alright, so I resolve T1 and T2 into their x and y components. T3 only has a y component, so I don't have to resolve it. So here's Newton's second law in the x direction for the knot. In the x direction, you've got T1 acting in the negative x direction, T2 acting in the positive x direction. So it's going to look like T2x minus T1x equals 0. The knot is also stationary, just like the stoplight. So we've got T2 in the x minus T1 in the x is equal to 0. Now this has two angles which we know, but it's got two tensions which we don't know. So I'm gonna make a system of equations in order to solve for T1 and T2. F net and the y, I've got the y component of T1 and T2 acting in the positive y direction. Okay, T1 and T2's y components are pulling up on the knot. T3 is pulling down on the knot. So T1y plus T2y, right? They're both acting in the positive y direction, minus T3, which is acting in the negative y direction, equals 0. Again, when I'm calculating the forces, right, or if I'm writing expressions for the forces, I'm writing expressions for the magnitudes. All right, magnitudes only. I'm not giving them negative signs because I don't want to accidentally give them a negative sign twice. So I wait until I write Newton's second law and give any force acting in the negative direction a negative sign with it. Okay, that's how I personally like to handle it. So we've got two equations, two variables, we can solve a system. So I'm going to take F net in the x direction. You could solve it for T1 in terms of T2, or you can solve it for T2 in terms of T1, whichever you want to do. I'm going to solve it for T2, and I'm going to get an expression for T2, and it's going to have T1 in it. So whatever I get for T2, I'm going to plug in here, right here, in my F net in the y direction, and then I'll know everything else and I'll be able to solve for T1. So I'm going to add T1 cosine theta 1 to both sides, and I get this here. T2 cosine theta 2 is T1 cosine theta 1. Divide both sides by cosine theta 2. I've got a nice expression for T2 in terms of T1. This is substitution from our algebra days, right? When you had two or more equations, two or more variables. So I'm solving for T2. I'm going to substitute it in here. So T2, I'm replacing with T1 cosine theta 1 over cosine theta 2. So here it goes. It's this thing right here. T1 cosine theta 1 over cosine theta 2. I'm also doing something else. I'm doing two things. So I'm substituting this in for T2, and I'm also adding T3 to both sides, because I know what T3 is. T3 is a number. I'm eventually going to substitute it in there. Alright, so both of these terms have a T1 in them. So I'm going to factor a T1 out from both sides on the left side of this equation. Factor out a T1. I'm left with sine theta 1 plus cosine theta 1, and these two terms right here, I've got a sine theta 2 in the numerator, cosine theta 2 in the denominator, right? As long as they're the same angle, I can write them as tangent theta 2. Okay, so this tangent theta is this sine over cosine term right here. Okay, so that's all in parentheses. I factored out a t1. I still have t3 on the right side. Divide both sides by this whole thing in parentheses to get t1 by itself. Notice we have both the angles that we need, so we can calculate this. We've got t3, so once we get t1 by itself, we can calculate it. So it's t3 over sine theta 1 plus cosine theta 1 times tangent theta 2. Okay. Plug our values in. I've got 122 newtons. Theta 1 is 37 degrees. Theta 2 is 53 degrees. And I get a tension in T1 of 73.4 newtons. Again, this is the magnitude of the vector. This is the tension in T1. So T1 shouldn't break. Right? It's less than 100 newtons, so we should be okay. Now that I have T1, this is why I like the substitution method in most cases. I've already solved for T2 in terms of T1, so I'm going to come back up here. I have the angle still. I can plug 73.4 newtons in here for T1, plug my 37 degrees in for theta 1, 53 degrees, that's a typo, so I might be a little bit off here. 53 degrees for theta 2, calculate that, I get T2 of 97.4 newtons. Again, less than 100 newtons, so the cable should not break. Alright, recap, Newton's second law in two directions, right, two dimensions. Write Newton's second law in the x, write Newton's second law in the y. If there are any vectors acting in the x and the y direction, make sure you resolve them first before you substitute them in your Newton's second law equation. And if you don't have enough information to solve one equation for a variable, use this system approach, do the substitution. Sometimes linear combination is a little bit easier. I always stick with substitution because I'm comfortable with it, or I try to anyway, unless it's clearly more straightforward to do a linear combination method. Okay, the rest is just algebra. Once you get Newton's second law, I solved for the two missing variables, and that was it. Alright, so this is an inclined plane problem, but we're starting off with a frictionless surface. We're gonna devote a whole slideshow and a whole set of videos to friction, but for now we're going to deal with surfaces that are frictionless. There are no surfaces that are truly frictionless. The friction is just low enough that it's negligible and we can ignore it. Alright, so you're pulling a 2 kilogram snow sled. This is a little bit different than the stoplight because I'm giving you the mass of the object. So we're going to have to use m times g to calculate the weight force on the sled. So you're pulling the snow sled up with a force of 15 newtons up a 20-degree frictionless hill. So that's the angle of the incline. I'll draw a picture and a free body diagram. What are the sum of the forces in each direction? And what's the sled's acceleration? So we need F net in the x, we need F net in the y, and the acceleration. So here's my picture, right? Here's your sled. Actually, what I'm going to do is I'm going to take a break here. I'm going to stop before I actually do the sled problem. I forgot I had a couple extra notes here. So I'm going to talk about how we set up an inclined plane free body diagram that's on a frictionless surface. Okay. So right now this is just an object sitting on an incline. Nothing's pulling on it or pushing it down the incline. So we've got, it's frictionless still. So we've got gravity which acts in the negative y direction. Right? Even though this is on an incline, gravity is going to act in the negative y direction. The normal force is always going to be perpendicular to the surface. So if you notice, the normal force is not pointing opposite the gravitational force, so we have to account for that. What we're going to do is we're going to do something similar to what we did in chapter 2. We're going to take our coordinate system and we're going to rotate it an angle theta counterclockwise, so the x-axis is again matching up with the incline. Alright, and the reason we do this is because we are going to have to split a vector up into its x and y components. But when we change our coordinate system here, this allows us to resolve the fewest force components, right? Because if you have something pulling down the incline or pushing up the incline, those are already going to be in the x direction, okay? And now that we have our coordinate system tilted, our normal force is in the y direction. So the only thing we have to worry about resolving is the gravitational force. So we're going to do that now. We're going to resolve our gravitational force into x and y components. First thing I'm going to do is I'm going to take the gravity vector, the slope of the incline, and I'm going to make a right triangle out of it. All right. See this right here? I'm making a right triangle. So I drew that right triangle. Theta is the angle of the incline. The angle made by the gravitational force vector and the incline is theta's complement. Right? What does complement mean? Theta and phi add up to 90. So if I know what theta is, I know what phi is. In this case, in the sled case, theta was 20 degrees, I believe. Okay. So in this example, I know phi is 70 degrees. Okay. Phi is 70 degrees. Okay. But it can be anything. It really just depends on theta. So this angle right here is theta's complement. So I'm going to split f sub g into its y component. I'm just going to draw it on the free body diagram. The y component goes along the negative y-axis. The x component goes along the negative x-axis. Down the hill is negative. We can switch that around if we want, if it makes our lives easier. But for now, down the incline is negative. Okay, so I've got f sub g, its y component, and its x component. The angle that the y component of the gravity vector and the incline make is 90. Okay, this is a right angle right here. So that means, see this triangle right here? This triangle right here? I'm going to make a new right triangle with the hypotenuse is the gravity vector. Okay, so my right angle is going to be down here. Right? I got side, side, hypotenuse. This angle right here is phi's complement. This angle right here is phi's complement. Phi's complement is theta. So I know this angle right here is theta. So I'm going to draw a new right triangle, FGY. The hypotenuse is f sub g. There's theta. I'm going to take f sub g in the x direction and I'm going to bring it down here and I'm going to make a right triangle with that. Okay. So my x component is one side, my y component is one side. Here's the problem. I like theta. I like the angle that they give me. But now the adjacent side to that angle is FG in the y direction. The opposite side is FG in the x direction. So guess what? Our trig functions change. Right? The y component of the gravity vector is the cosine. The x component is the sine component. Alright? So my advice to you is just commit that to memory. I'm normally not a proponent of memorizing things per se, but commit these two to memory. When you're on an inclined plane, you always have gravity acting in the towards the surface of the Earth based on our coordinate system. Now the y direction is the cosine component, the x component is the sine component. All right. It doesn't really do us good to you know, rigorously derive this whole set of right triangles every time. Okay, so just keep in mind that your trig signs are flipped for the gravity vector. Okay, so now I can write f net in the x direction and f net in the y direction. F net in the x direction is just the x component of the gravity, right? So gravity is pulling it towards the incline, but a component of gravity is also pulling it down the incline. Okay. So in this case it's negative f sub g in the x direction, negative f sub g sine theta. Remember that gravity is mass times the acceleration due to gravity. So my expression for the net force in the x direction is negative mg sine theta. F net in the y direction, you've got the normal force, which is acting in the positive y, and the y component of the gravity vector. So I've got the normal force minus the y component of gravity, which is normal minus fg sine theta. Again, f sub g is just mg. Most of the time, this equation, f net in the y direction for an inclined plane problem, the sum of these forces is going to be equal to 0. As long as the object's not leaving the incline or nothing else is pushing up and down on the object on the incline, these are the only two forces acting in the y direction. There's no motion in the y direction, so that's equal to 0. Okay? So this is how we handle an inclined plane. And later on we're going to have applied forces, right? The sled, you're pulling up the incline, so we're going to have another force in the x direction. We could have friction going up or down the incline. Again, we'll talk about that more thoroughly in the next section. Okay, but you're always going to have gravity and the normal force, and then we'll add some more forces later. So now on to our sled problem. We got our free body diagram. We've got the normal force. We've got the force due to gravity in the y direction, force due to gravity in the x direction. We've got a fourth force now, the applied force up the incline. So you're pulling the sled up the incline with a 15 Newton force. So I've committed these to memory. Gravity in the x direction is mg sine theta backwards. F sub g in the y direction is mg cosine theta. Okay, so these are the expressions I'm going to substitute in my Newton's second law problems. Alright, so it's two dimensions. Got to deal with F net in the x, F net in the y. F net in the x, up the incline is positive, F sub a is positive. The x component of gravity is negative, Fg sine theta is negative. Okay, that's equal to ma in the x direction. Alright, we're being asked for the acceleration of the sled, so I've got to have some acceleration term somewhere. We're going to assume that they're talking about some acceleration in the x direction. There's not going to be any acceleration in the y direction because the sled is sliding up the incline. It's not leaving the incline or anything like that. So in the y direction we've got the normal force, which is the positive y direction, gravity in the y component of gravity in the negative y direction. So F sub n minus Fg cosine theta is equal to 0. Equal to 0, there's no change in motion in the y direction. Okay. So this is actually another typo. Sum of forces in the x direction. F net in the x direction is ma. So that corresponds with this right here. Sorry about that typo. So what I'm going to do is this has everything, right? I think I could use this to solve for the acceleration of the system because I've got m, I've got g, I've got theta, I've got the applied force. Let's just solve F net in the y direction just for the future because we'll need this term. All right, normal minus the x component or the y component of gravity, F sub n minus mg cosine theta is equal to 0. Add this term to both sides. I know the normal force. Again, I'm not asked for the normal force, but this is going to come in handy later. So the normal is not equal to mg now. It's equal to mg cosine theta. Take a F net in the y direction and I can solve for the acceleration in the x. I know everything else in this equation. Okay, so divide both sides by m. I've got F sub a minus mg sine theta over m. Plug your values in and you get an acceleration of 4.1 meters per second. My acceleration is positive, so that tells me it's accelerating up the incline. Okay. So F net in the y direction is 0. Okay. F net in the x direction is the object's mass times its acceleration. All right. So I don't have to plug this in and then calculate this and add them together. If I know the acceleration and the mass, I know the net force in the x direction. So just take the object's mass, multiply it by the acceleration you got prior, and you get the net force in the x direction. Okay, I did that without calculating this individual force. Okay, I did the same thing in the x direction. Right, I know they're equal to 0 because there's no acceleration in that direction. Okay. Okay. And alright, so we're going to do two more problems. We've got two problems that are systems, right? System of objects. There are two or more objects that are connected together. So there are there's one assumption that I can make. All right, any objects that are connected by a string or a cable, or they're in contact with each other, they're going to have the same acceleration. Okay, so they're going to move at the same rate. Whatever the forces are acting on the system are going to change their acceleration at the same rate. So that's going to be useful. We're not going to have two different accelerations. So M1 is 4.2 kilograms. Again, this surface is frictionless for now. And then M2 is 11.6 kilograms. Okay. Now I predict what's going to happen is, let's say I'm holding on to M2, let go of M2, M2 is going to descend. Right? I'm making that prediction solely based on the fact that M2 is much greater than M1, and also, we don't know this, but there's no friction. Right? There's no friction, so M2 is going to descend and M1 is going to travel in the positive x direction. That's what I expect to happen. So when we want the acceleration of each object and the tension in the cable. All right. So for now, the tension is everywhere, or is the same everywhere. All right, in this cable. So I'm just looking for 1T. So I'm going to draw a free body diagram for M1 and a free body diagram for M2. Okay. Free body diagram for M1. I've got M1G. I've got gravity acting in the negative y, the normal force acting in the positive y. There's no friction, so the only force acting in the x direction is the tension. All right, the cable is going to pull M1 in that direction. M2 is suspended in the air, no forces in the x direction. There's just gravity, M2G acting in the negative y, and then there's tension acting in the positive y direction. Okay, again, tension is the same everywhere. Okay, for now, tension's the same on this side of the pulley and this side of the pulley. All right, the acceleration of the two blocks is going to be the same. All right, they're connected by the cable, and they're going to have the same acceleration. So what happens is M2 is going to move in the y direction and M2 is going to move in the x direction. But I want all my signs to match up, so I have to pick a coordinate system that's different for one of the blocks. So this direction, right, to the right for M1 over the pulley and down for M2 is positive. All right, because I want these signs to match up, otherwise I won't be able to solve the equation. All right, so to the right is positive for M1 and down is positive for M2. Okay, so we want M2's acceleration to match M1's acceleration. So we'll say down is positive for M2. All right, Newton's second law for M1 in the x direction. It's just T. Good. So T is M1 times A. That's the acceleration for M1. In the y direction, there's no acceleration, so the normal minus the gravitational force is equal to 0. We can see that we can solve this, right? We can solve this for normal force. We're not being asked for that yet, but this will be useful. M2 only has forces in the y direction. Again, we're picking down as positive for M2. So gravity minus the tension for M2. M2G minus the tension is M2 times its acceleration. Again, these A's are the same. Both objects are going to have the same acceleration. So just for fun, we can take this equation, plug it in there, solve for the acceleration. Right? I've got T already solved in terms of acceleration. I can plug it in there, solve for A, do the substitution method, get the acceleration, come back here, substitute the acceleration in, solve for T. Go ahead, if you got spare time, have fun with that. I'm going to avoid this in this case. In these last two problems, I'm going to show you a little trick that helps me avoid solving multiple equations. And that's this. If both of them have the same acceleration, the tension is the same everywhere, they're both going to move in this direction, right? M1's going to move to the right, M2's going to move down. So I'm going to put my little system bubble, right? I'm going to draw a box around M1 and M2. So I'm going to combine M1 and M2 as one system, and then I'm going to write Newton's second law for that system. Now what happens when I draw my box around this whole system, any forces that are inside the box are now internal forces. So when I draw my circle around, right, when I draw my circle around these two blocks, the tension is inside. So that's not a force that's causing the system to accelerate. Tension is just acting on the individual blocks. So here's what happens when I draw my circle around. There's only one force acting on the system that's causing it to accelerate. Right? T is now contained in my system. So it's just M2G. These two forces aren't causing M1 to accelerate. It's just gravity on M2. Alright. So M2G is the only force acting on the system. But it's equal to the mass of the system times the system's acceleration. So when I do my system box, the mass of the system is the sum of all the masses of the objects inside. Alright, so this is the mass of the system, M1 plus M2. But I know the masses, I know the acceleration due to gravity. I'm solving for A. This helps me avoid this substitution issue I have over here. So I can get an acceleration, divide both sides by the mass of the system, M1 plus M2, and plug your values in. I know the masses, I know G. I got the acceleration of the system, which is 7.2 meters per second squared. That's positive, which matches my prediction, right? M2 is going to descend, which I said was positive. M1 is moving to the right, which I said was positive as well. Okay, so a positive 7.2 meters per second squared. Now I can come back here, plug that value in for the acceleration, solve for the tension. I get 41.2 newtons. So this is how I just avoid solving a system of two equations up here. All right, if you're comfortable with it, it's fine. I like to use the system approach because I think it's easier for me. Okay, so let's do 3 blocks. Let's do our 3-block system. Very, very similar situation. Fortunately for us, all the objects are moving in the same direction. Okay, so I don't have to change any coordinate systems. So I got 3 blocks, 3 nice masses, 1 kilogram, 2 kilograms, 3 kilograms. Okay, there's an applied force acting on M3. This is my applied force vector. It's being applied to the 3 kilogram block. But here's what happens. M3 and M1 are connected by a cable. We'll call the tension in that cable T. M1 and M2 are in contact with each other. So if you picture this problem, you pull M3 along, M1 and M2 are going to come along with you. Alright, so all 3 of these objects have the same acceleration. Once I'm done with free body diagrams, I'm going to draw a circle around all 3 of these, and then I'll write Newton's second law for that entire system. So free body diagrams. For M1, I've got the normal. I've got gravity. Notice all of these, right? M1, M2, M3. They all have normal due to the surface and gravity. Normal, gravity, normal, gravity. Okay? So there are 3 separate normal forces on each block, 3 separate gravitational forces on each block. Now let's talk about the x direction. For M1, we've got the cable attached to it, so we've got T acting in the positive x. But as this moves, M2 is in contact with it, so M2 is going to push against it in the negative x direction. So I'm going to call this F by block 2 on block 1. So by 2 on 1. That's in the negative x direction. We're actually asked for that, right? The force exerted by the 1 kilogram block on the 2 kilogram block. Well, that's by the 2 on the 1, right? So that's not the actual force that they're asking for. But when we draw the free body diagram for M2, we see that it's got normal, gravity, y direction, but M1 is pushing on it in the positive x direction. That's what's causing M2 to accelerate in the positive x direction. So I'm going to call that F by 1 on 2. Alright, so that's what I'm being asked right here. Alright, M3, you've got the applied force in the positive x, and you've got the tension in the negative x. So we got to solve for the tension here, which is the same here, same cable, same tension. Got to solve for the tension, solve for the acceleration, and then solve for this force right here. Newton's second law. Let's start in the y direction, right? Because they're all the same. Normal minus gravity is 0. Normal minus gravity is 0. Normal minus gravity is 0. None of this stuff we need right now. But again, add the gravity terms to both sides, you can get an expression for the normal force. Okay. Don't need it now, but it's still going to come in handy. X direction for M1. We've got tension minus the force due to block 2 is equal to M1A. For M2, the force due to the 1 kilogram block is the only force in the X direction, equal to M2A. For block 3, you've got the applied force, which we know, minus the tension is equal to M3A. So now I really want to use my system approach because I do not want to solve 3 equations for 3 variables. I can do it, but I don't want to. All right. So I'm going to draw my box around all 3 blocks. All right. Same thing as the last problem. I've got the tension. The tension's now inside the system. So the tension is an internal force. I don't have to worry about that when I write Newton's second law. So what's the mass of the system? M1 plus M2 plus M3. Cables are massless. We're going to assume cables and pulleys are massless. So the total mass of the system, 6 kilograms. What's the only force causing this 3-block system to move? F applied, which we know. That's great, because I can write one Newton's second law problem in the X direction, because I don't care about the Y direction. It's not accelerating in the Y direction. Newton's second law in the X direction is F applied equals the mass of the system, which is the mass of all 3 blocks, times the acceleration. I know the applied force, I know the system's mass, divide both sides by the system's mass, and I've got the acceleration of all 3 blocks, 5 meters per second squared. Much easier than trying to solve a system of 3 equations up here. Okay? If you want to, for fun, you have some time, go ahead and give it a shot. But this is my proposed method of solving this problem. Now we've got an acceleration. So that means I know this, I know this, I know this. Right? So I'm going to go a little backwards here. I'm going to find the force of block 1 on block 2. That's what's being asked. Okay? Substitute the acceleration in to this thing. So even though we aren't using these to solve for the acceleration of the system, they're still going to be necessary, right, when we're looking for individual forces on each block. All right, so they're still good to write out because they're going to come in handy. Plug in the acceleration, 5 meters per second squared times a 2 kilogram block. The force by block 1 on block 2 is 10 newtons. What else is a force of 10 newtons? The force by block 2 on block 1. This is a Newton's third law pair. These are 2 objects in contact with each other. It's the same type of force, opposite in direction, equal in magnitude. Okay? So this is a third law pair. So F1 on 2 is 10 newtons, F2 on 1 is 10 newtons. We don't need this, but it's good to know. All right. So we could actually do 2 things, right? We know F1 on 2 now. We know the acceleration. So you can either use equation 1, Newton's second law in the X direction for M1, or Newton's second law in the X direction for M3 to solve for the tension. Okay. I used equation 3 to solve for the tension. You can use equation 1, whichever one you like. Add t to both sides. Subtract both sides, or subtract m sub 3 times a from both sides. So I've got t by itself. It's the applied force minus m3a. Again, I know the acceleration of the system, mass of the 3 kilogram block. We were given the applied force, and I can solve for the tension. Alright, so recap. We've got this system of multiple objects. Still want free body diagrams for each object. We still want Newton's second law for each object. 2 or more objects, you're going to have a system of variables. Maybe you'll be given enough information to where you won't have to solve a system of equations. Right? Maybe you could just solve this, solve for the tension, come over here and solve for something missing. Right? Always explore this approach. Draw a box around all the objects that are accelerating. Reduce the number of forces that are acting in the X direction for the whole system. Okay, so that's gonna reduce the number of forces that you have to deal with if you can isolate forces inside your system box. You're going to get an equation, a Newton's second law equation, that's going to be much easier to solve, and you could avoid solving this system. Okay, so always look for that approach. See if you can solve for something using the system model. Okay. All right, so that's the end of the first part of chapter 4. I'm going to start with friction. I'll introduce friction, get those uploaded as soon as I can. All right, thanks.